Hello. Today I'm going to talk to you about metering, monitoring, and targeting. Metering, monitoring, and targeting, or MM&T for short, is a process or a system of management that allows you to manage your energy consumption, costs, and carbon performance effectively. It's inconceivable that someone would set off on a car journey, say from Belfast to Dublin, in their car without knowledge of how to drive that car, the route they plan on taking, a fuel gauge, a speedometer, and some sort of mechanism to advise them of dangers. Well, surprisingly, this is the automotive analogy of how many companies manage their energy and carbon efficiency. The automotive example given is a useful parallel. If you drive a well-planned route at a sensible speed in a well-maintained car, you would inevitably use less fuel and have a lower carbon footprint than you would without that planning. However, understanding exactly how you're driving relies on there being some instrumentation and performance measurement available to the driver, and that is exactly the principle that we are trying to apply with metering, monitoring, and targeting. MM&T is, if you like, the equivalent of instrumentation that a modern car comes equipped with, except this is for your business. If the driver was well briefed and well equipped, they might be able to optimize their route to accommodate fuel stops or nowadays recharging arrangements and may care to drive at a speed that gives them the best additional marginal performance, using, for example, the cruise control fitted to a car, providing improved fuel efficiency. In the event that your car was experiencing reduced miles per gallon, you could query that performance. Similarly, if your business is experiencing a reduced energy performance, you could query the data to find out why. In the car, you would be able to predict the fuel consumption for a journey, and in your business, you could predict the energy consumption for a specific production period, allowing you to attach a cost and a carbon footprint. In the car, you could make allowances and considerations depending on the type of driving you were planning to do, whether that be on the motorway or in an urban area. In your business, there are economies of scale that can be applied to long production runs, and we need to understand what the business impact of those economies of scale are. You may, of course, care to drive more sensibly when you're able to understand clearly how much fuel you're using. And once again, there is a parallel to a business that can be drawn here where we might choose to operate equipment more optimally if we could see how much energy, cost, and carbon was associated with that operation. If we made improvements to our car, such as having the engine changed, the tires pumped up, and so on, then we would inevitably see that benefit materialize in the MPG figure if we keep a consistent track of performance. This is also true of a business. If we keep a simple track of energy performance and make appropriate improvements, then we will see that benefit in the business MPG or key performance indicator equivalent. If I have a reliable MPG figure from my car, I can compare that on an ongoing basis between when the car was new and how it performs as time goes on. The same is true of a business. You can observe performance through KPIs such as kilowatt hours per widget from when the plant was first commissioned, and then analyze that performance over a period of time and detect variation or change not just related to production volume or changes, but aging in general. This process is called internal benchmarking. You could also consider your car in comparison to other similar models and look to see whether your car is performing as per its expectation, and this would be a process of external benchmarking. Equally, you could compare the performance of a Ford Focus with the neighbor's Jaguar and quietly know that the Focus was spending an awful lot less on petrol. The same is true of the business. I can both internally benchmark and externally benchmark, which allows me to understand my competitive position in the marketplace in terms of energy cost and carbon footprint. MM&T is a system that allows you to manage your energy, cost, and carbon footprint. Initially, you would have to measure quantities such as fuel, power consumption, and production, and from them derive a set of KPIs which are kilowatt hours per unit of production, or carbon kilograms emission equivalent per unit of production, and use these production-related KPIs to understand the business performance. It should also be said, of course, that energy and carbon are one of a number of overheads in a business, and labor or material costs and many others might be examined. If you establish a clear understanding of the business performance and understand the fixed and variable consumptions, those that are directly or indirectly related to production. This will allow you to make a very accurate decision-making platform which will allow the business to run more cost-effectively with a reduced carbon footprint. The implementation journey is probably best understood by the diagram below. If we were to consider most businesses which go about production in the way that they always have, there will be associated energy consumption, cost, carbon footprint, labor input, and so forth. There are almost always opportunities for optimization. It is a simple fact that not all industrial processes are well controlled, and so we may have a background performance illustrated here by box A. As long as we can identify and quantify that existing performance and the variations involved, the first step of MM&T is intended to gain improved control of that process and move from A to B. The performance illustrated at B in this example shows that the energy consumption per unit has not gone down, but the variability has reduced and our performance management has improved. Thus, we can produce the same goods for the same amount of energy more consistently. This is a good first step with any energy cost or carbon management system. Of course, as time goes by, particularly when we've got good metering granularity and an understanding of the individual processes that go to make up a global site performance indicator, we can start to look at specific optimizations, which, if we were to use the automotive analogy, might be a new set of tires or an engine tune-up. This is where we move from B, where we understand and control in an improved manner, to point C, a situation where we still retain the level of control repeatability and consistency, but also achieve our production at a lower specific energy cost, and a lower specific energy cost generally means lower monetary cost and a lower carbon footprint. There are a wide range of analytical techniques available to assist in performance evaluation. These include, but are not limited to, mean and range tracking, regression-based analysis, which allows you to take into account volume influence if that's a significant factor, marginal cost, or consumption curves, which we can use to determine the optimal minimum and the optimal maximum operating points of a business in terms of volume of production. Finally, and most importantly, we have what is called a cumulative sum of errors, or Q-sum. Q-sum really is a most powerful tool in the analytical toolbox, and one that we'll come back to shortly. However, for any and all of these techniques, it is vital that we understand what our target performance is. Is our target valid? Is it relevant? How was our target determined? In the first instance, the target is simply historical performance. The target, of course, is very, very important, and the initial target should be the performance during a historic period that reflects normal or expected production ranges. In your production, for most businesses, there will be a normal expected range of production activity, and it is important that the target period reflects that. However, it is equally important to ensure that the target period is not one in which there is very significant overall production growth or expansion. Otherwise, we're going to end up operating on a different point of the marginal performance curve, and our target will essentially be irrelevant. Warts and all, it is important to realize the full performance range, and as such, it should be screened for obvious outliers. The time frame for measurement will depend on what's being measured. If you are measuring a global performance indicator, a company's overall electrical or fuel performance, then a weekly or monthly interval might be more adequate. However, if you're measuring with a high degree of granularity and looking at the kilowatt hours per widget on a specific production line, then hourly or daily might be more appropriate. It's impossible to give generic guidance on this, and it's a matter for inspection, examination, and subsequent determination. We will be able to give you an appropriate time frame for measurement depending on the level of detail that you want to achieve in setting a target. For most businesses, and for a more generic overall performance indicator, such as total fiscal kilowatt hours per unit of production or fiscal gas consumption in kilowatt hours per unit of production, then a weekly or monthly time measurement basis is usually sufficient. Returning to the analytical techniques, the first of these, the mean and range tracking, is least complex. Essentially, If we identify a relevant period of historical data, and then we derive the average or mean for that data, we can look at an ongoing performance against that mean, as can be seen in this slide. Here, month by month, our kilowatt hours per widget is sometimes slightly above or slightly below our mean performance, but is on track overall because the points above and below the mean bring us back down close to the historic value. We would look at this chart and not see a significant performance issue. Taking this a step further, we could perform some basic statistics on the data and come up with an upper and lower limit of expected performance based on standard deviation from the mean. Standard deviation tells you how spread out the data is. It is a measure of how far each observed value is from the mean. So we might set +1 standard deviation above the mean and -1 standard deviation below the mean as guides to understanding our performance. When measuring ongoing performance, should it fall above or below these standard deviation-based limits, we would take a closer look to understand why the performance has changed so drastically in those specific months. It's a simple concept relying solely on a historical mean and doesn't take into account any impact from volume of production. Therefore, it has its limitations, but for many business applications, particularly for global performance indicators such as overall site power or gas consumption, where we aren't looking at a specific process, this can be very useful. To give some perspective to this, we have extended the example from the previous line to include a second year, where optimization has taken place and now most of the performance plots are falling well below the historic mean, which we can see visualized in the graphic. This is ideal, as most of the performance in the second year is well below the mean and even 1 standard deviation below, which suggests that we have made a business optimization which has worked and is being sustained. This example, of course, is fictitious and has been deliberately manipulated to show a performance improvement in the second year. Often, however, it is not as clear or as obvious as indicated here, and interpretation of the mean arranged chart requires skill, effort, and statistical knowledge. Using Q-sum, or cumulative sum of error from the mean, we can understand whether we are collectively winning or losing. If you were consistently improving performance, all of the performance plots would be below the mean, and the cumulative sum would slowly become negative because there would be more good performance figures than bad. We can plot this cumulative sum of error and easily understand from the slope whether we are winning or losing. In this slide, the Q-sum, or cumulative sum of error for the mean for the preceding example, where the performance was deliberately improved for year 2, is shown. What we can see is that in year 1, although there is variation, essentially the gradient of the best fit line is 0 and is flatlining. In year 2, however, the gradient of the best fit line is sloping down, and here the change in gradient is telling us that we are continuously improving. A shallower gradient would suggest that we are making a consistent small saving. A steep gradient would suggest a considerable saving, and a change in gradient is indicative of a change in the performance. The Q-sum is a quick and easy way of interpreting mean and range in addition to other analytical charts and in addressing energy and carbon performance. Looking now at some of the other analytical techniques that we may use, regression analysis is quite a common technique which requires great care to utilize properly. It is a very powerful technique, but the data being used must be validated to ensure that it lends itself well to regression analysis. If the data does not, the results will be misleading. A regression model is able to show whether changes observed in one variable are associated with changes in another. For example, kilowatt hours per kilogram, kilowatt hours per liter, or kilowatt hours per widget. To put this into perspective, if we plotted 2 points of performance on this graph, we could draw a straight line between them and demonstrate a regression. Of course, the 2 points may be completely unrelated, and the straight line would provide a skewed picture of the actual performance, and this is why it is so important to take good care. The use of regression in the graph relies on there being adequate correlation coefficient in the data points. This is a routine activity for Element consultants, and we can assist you to formulate a thorough and correlative regression for your business activity. In the example below, you will see that as production increases, so too does the gas consumption in this particular graph. To illustrate the point, the correlation here is exceptionally good. In the regression analysis, in most cases, it is usually possible to define a relationship, here shown as a straight-sloped line. Where that relationship is well defined, we can use the slope of the line and the point opposite on the vertical axis to determine the relationship of the data points. For example, for any given production volume, using the route A, B, C on the diagram, we can determine any unexpected or target energy consumption. It is almost always the case, particularly so with very high-energy industries such as metal casting, steel smelting, or glass manufacture, that there is an element of energy consumption which is not directly related to production volume and is always present. For example, in a high-temperature furnace, heat losses are constant regardless of how much glass is produced. Once a regression has been established, that is reflected in the point on the vertical axis where the slope line crosses. In this example, the dark pink indirectly related fixed volume of consumption. This indirect consumption tends to be associated with things like compressed air leakage or other items that can be optimized. The remainder of the consumption is directly production related. As the volume increases, so too does the energy consumption. It is an inevitable part of any industrial activity that there are fixed losses, which is obviously undesirable. However, understanding what those fixed losses are and minimizing them is an essential part of managing energy costs and carbon footprint. To recap, the historic relation that we establish is that between the volume of production and the volume of energy consumption over a specific period of time, which could be a month up to a year depending on the process and degree of granularity required. That correlation can usually be defined in a straight line relationship. This analysis can help us quantify baseload and losses, shown here in dark pink, and those which are directly production volume related, shown in the pale pink triangle. To illustrate the point, if you were able to reduce the baseload energy consumption, for example by curing system air leaks or similar means, a new set of performance figures would be derived. These would produce a sloped line that sits below our original sloped line, indicating lower energy consumption per unit of production. You may also gain benefits of scale from some optimizations, and in that case, the slope of the line will also change. When you use a regression analysis as the analytical tool, what you want to see is the line representing the new performance well below the original and, possibly, a slope change. We've talked about target setting. We've talked about the basics of MM&T, we've talked about some of the analytical methods that might be used, and we've talked about timeframes and granularity. Metering equipment is now considerably less expensive than it was only a few years ago. It is absolutely true that you are unable to save what you don't measure. You just don't know where or how it's being consumed, and it's not possible to make an effective judgment or implementation on how to improve that. As such, with the relatively low cost of metering, it is important to meter effectively and to improve the granularity of your measurement. Granularity meaning the number of meters as well as the time basis on which you measure. For example, if we measure on a half-hourly basis and integrate to a daily or weekly basis, we are going to have a much improved picture of consumption and the ability, when we detect an anomaly, to go in and investigate more thoroughly if we have a higher degree of metering granularity. Finally, an action plan must be established to deliver MM&T. The first step is to identify and employ a data engineer with suitable specialist skills who can provide an overview and screening of the likely energy and carbon cost relationships and the structure that will be required. This will inform the data collection hardware design and installation plan. A short specification for the system, the analytics, and the hardware should be developed. The software architecture should be discussed and agreed upon with a competent data engineer. Creating a bespoke MM&T system that is specific to your business is unlikely to be achieved through a proprietary system. You are unlikely to be able to manipulate the design and data for your specific requirements. Element consultants have written much of the guidance available on metering, monitoring, and targeting. We have experience producing MM&T systems for some of the largest companies in Northern Ireland and the UK. We can provide our services as a back-office type service, or we can simply provide guidance and support as described in this presentation to a client who wishes to build their own
totally unique MM&T system.